All right, good morning. Let's take a look at one of my favorite problems. So this is problem 77 from chapter 6. It is a frame. We know that because there are some multi-force members. For example, AC here, right, has applied moment, so that's clearly a multi-force member, and BDE here also has forces applied at B and D and E, making it a multi-force member. So we have a frame because there's no motion, it's meant to be static, and there's multi-force members. This is a 2D rigid body equilibrium force because the forces do not intersect, and it is coplanar, so we're dealing with 2D rigid body equilibrium. We'll draw the 2D free body diagram, we'll apply 3 equations of equilibrium, and move on from there. All right, so we are, let's clear that off. And let's, we want to find forces at A, C, D, and E. Okay. And let's make that pen a little bit smaller. There we go. Let's write down that we're assuming 2D rigid body equilibrium. All right. I'm going to start with, typically with frames, we're going to start with a free body diagram of the entire object. Because I'm working on a screen, I have the opportunity to kind of trace the body. Okay. And then I can select that and drag it over here. Drag it over here. And that looks good. All right. So the body is drawn here. It doesn't include the pin, it doesn't include the moment or the connections to the environment, it just has the full frame shown. And then let's throw a coordinate system on there. Standard XY. And let's talk about those loads. All right. So down here, A, AY, AX. At E, that's a pin. EY, EX. D is a roller, just resisting the downward motion. We also have some knowns. So 500 pounds out here at B. And 600 pound-feet at A. So that means that we've got all of our loads with magnitudes and directions. The coordinate system's done. We do need to include some dimensions. All right, so let's see here. If we start from A and work our way over, dimension over here to D is 3 feet. Oh, plus 3 feet. So let's fix that. That's going to be 6 feet. All right, and then we've got another 2 feet over to E. Okay. We don't need any, we do need the elevation of EY. So that's going to be 4 feet. All right. So it looks like for this free body diagram, everything's set up so we can write our equations of equilibrium. All right. I'm going to scroll up for a second. We'll come back. All right, so sum of forces in X equals 0. We have AX plus EX. And that's all in the X direction. Two equations, or one equation and two unknowns. Sum of forces in Y equals 0. dy plus dy plus EY minus 500 pounds. Okay, so now we're at two equations and 5 unknowns. If I sum moments about A, we get nothing from AX or AY. We get nothing from the 500 pounds. That comes right through A. So we're going to do positive Vy times 6 feet. That's going to give us that counterclockwise rotation. Plus EY times 8 feet. Again, counterclockwise rotation, so that's positive. Minus, because EX is going to cause clockwise rotation, EX times 4 feet. So at this point, we have 3 equations. 1, 2, 3, 4, 5. Double, double, double. 3 equations, 5 unknowns. Which means when we go to all our unknowns solved, we're in a no, so we need to identify another body. All right, so when we're selecting which body to go with, we want to pick which one has fewer unknowns. So AC, undo. AC has unknowns at A and C. The connection at C is a pin, which is going to be a single unknown. So that's only 3 unknowns. So that's a better place to start. Where if we did BCD, then we'd have a single unknown at C, a single unknown at D, and 2 unknowns at E. So that would be 4 unknowns. So we're going to start with the unknown at AC. Actually, that's not a bad idea. Okay. Over a bit. I apologize if you hear noises in the background. I have 3 kids here, and they are being loud. Okay. So remember AB. We still have AY as a vertical and horizontal reaction, AY and AX. It's acting on member AC exactly the same way that the pin is acting on the whole thing. There's no switching directions here. We still have the 600 pound-foot moment, but we also have a normal force acting on that slot. So this is the normal force at C. Let's go with, as this moment tries to push the member AC down, right? So this whole thing is trying to spin this way. This pin here at C is pushing back against it and stopping that rotation. So that's what we show on that force, the normal force NC, is we show the normal force is stopping the rotation. And if we zoom in on that, let's take a look at that reaction. Sorry, still get my hang of this. This pin here, coming out of the bar BCD, is sitting inside the slot. So as the slot, or as the bar is trying to rotate down through, this pin is pushing back up against the slot. It's not stopping translation side to side, so it's fully acting inside the slot against the bar. Okay. So we're looking at our all loads with magnitudes and directions shown. So we've got AXAY, we've got the applied moment, we have the normal force C, but we don't know its direction. We do know that it's going to be perpendicular to the bar, but really to do any math, I need more information than just perpendicular to the bar. So we're going to add on, we know that the bar itself is, let's scroll over, the bar itself goes over 3 and up 4, so the bar itself is a 3, 4, 5 triangle. You know what? Let's add that note right on there. Let's over, up, 3, 4, 5 triangle on the bar. So the perpendicular reaction is going to take that triangle and reverse it. This perpendicular force here is going to be, we're going to switch the rise and the run. So it's going to be a 3, 4, 5 triangle. So I'll add that in over here. Three, 4, 5. So 3, 4, 5 triangle on that normal force pushing up against this bar. So now I have all the loads with magnitude and directions. I've got the body. We're going to stay with the same coordinate system, and we need dimensions for moment calculations. I could use the 3, the 4, but in this case, life gets a little bit easier if we recognize that moments are perpendicular, forces times perpendicular distances. And if I just include that 5-foot dimension, the math is definitely easier. All right, here we go. Sum of moments about A equals 0. Okay. So if I'm summing moments about A, I have a positive moment due to the normal force at C multiplied by 5 feet. Okay. And then AX, AY do not cause any rotation around A, so it's just the applied moment. So that's clockwise or negative. Looks like we need to move. There we go. Minus 600 pound-feet. Therefore, the normal force at C equals 600 divided by 5, and that's going to be pound-feet divided by 5 feet, or 120 pounds. Okay. All right, I'm going to do some of forces in X and Y, and we'll just throw them up here. Be right back. Okay. So we have the normal force at C is 120 pounds, AX is 96 pounds, and AY is negative 72 pounds. So we still have to find the forces at D and E. So yes, here. So now we're going to draw a new free body diagram. We'll take a look at system BCDE. We'll write our equations of equilibrium and solve for our last 3 unknowns. All right, so I've got a clean spot here with re-showing my free body or my schematic. So let's set up our third free body diagram. Actually, this I do find to be the easier way, but at this point we do have we've solved for the 2 unknowns, so we could come back into here and we could solve AX or EX. We can come into sum of forces of Y, get dy in terms of EY, and then we could plug into the moment about A. We could actually solve all these because we're down to having just 3 equations with 3 unknowns. But honestly, it's going to be easier to solve the free body diagram of BCDE, and then we could verify using those top 3 equations. All right, so We still have our force here of 500 pounds at B. We're going to come back to C in just a moment. The force at dy is still vertical. Force at the pin E is the same on this member as it is on the entire free body diagram. That didn't change. Okay. All right. So the force at C, right? When we drew the free body diagram of AC, that normal force was pushing up and holding it from rotating down through. But now we're looking at the force on BC. So the force on BC is going to be equal and opposite to the force that was on AC. It's going to represent this moment and how it's translating into BCD as pushing down on that object. So we're going to have a force acting here on point C. And that force is going to be this normal force, which we've solved. That's 120 pounds. That is the normal force. And it's pushing down. It's equal and opposite to the one we had before. And that is also going to be 3, 4, 5. It's going to have the opposite triangle to the bar that it's perpendicular to. All right, so I've got my A, applied loads. I've got the magnitudes and directions of all of them. B, the body, totally drawn. Don't have any of the reaction showing, just the body. The coordinate system, we're sticking with the same one we included at the top. And let's add those dimensions. So I need to know that this is 3 feet. I can keep them the way they are, or I can add and show like 3 feet, 6 feet, 8 feet. This time I'm going to keep them. Right. And looks pretty good. Let's write some math. If I sum my moments about E, I can solve straight away for dy. I like to start with something positive, so we'll go with 500 pounds times 8 feet. That's going to give me a counterclockwise rotation or a positive moment. Plus 120 pounds. But I don't need all of it. I just need the vertical component, so 3/5. And that's a distance away of 5 feet. And then I'm going to do minus dy times 2 feet. Dy is going to cause clockwise rotation. All right, so the 500 pounds times 8 feet is 4,000 pound-foot. 72 pounds times 5 feet is 3,600 pound-foot, divided by 2 feet when I bring it over to the other side. So we get that dy equals 2,180 pounds. So it's pound-feet divided by feet. So sum of forces y equals 0 equals dy plus ey minus 500 minus 3/5 of 120. Let's add some pounds in there. And ey equals, the dy is going to come over to the other side as negative, so we're going to have minus 2180 plus 500 plus 72, get a negative 1,608 pounds for ey. And we'll sum forces in x. And we have ex plus 4/5 of 120 pounds. Ex equals negative 96 pounds. So what that means, as we're applying a rotation at A as 600 pounds foot, rotation at A, and 500 pounds out here at B, this roller at D is really doing a lot of work to hold that whole thing up. So we've got 2 kips, 2,000 pounds pushing down here at D. E is holding back, so it's pulling it back down here at E, but it's also a little bit side to side, pushing out as this rotation here is trying to push through. But really, compared to the forces in C and A, D and E, those forces, vertical forces at D and E are really significant, with this 500 pounds being full 8 feet away from the pin end at E. We can zoom out a little bit, take a look at the big picture. And there we go. So all the unknown reactions, the forces at AC, D, and E, we've got AX being 96 pounds and minus 72. DY is a vertical 2,000 pounds. E has minus 96, minus 1,600 in the Y direction.